welcome everybody to today's webinar. My name is Dan Combest, and today I'm going to be talking on increasing speed and stability of CFD simulations with HELYX Coupled. As always, I start with webinar goals. Today I want to introduce ENGYS's CAE innovations as they're related to coupled solvers. I'll discuss a little bit why coupled approaches are important to industry. I'll show some examples and potential benefits. And then I'll show how to leverage the coupled capabilities within HELYX and Elements. As always, we'll answer all questions at the end and continue via email post-webinar. With your actual webinar invite, you can hit reply with a question that'll go directly to me, and then I can follow up with developers, or I can even answer it directly. If you're already a customer and you have a question, you can go ahead and send an email to me, or you can send an email to support and we will answer your question. Before we get started, at the beginning of, when I ask people to register for this webinar, we typically ask questions. And with all the questions that, all the answers provided, it really made me think about a particular paper that I read a few years ago. And so this was an Aberdeen Group report from 2010 in which companies were asked to mention strategies that they use to improve product design. And so the replies from this survey were from best-in-class companies. So these are companies that continuously and frequently deliver on time, deliver products under budget, and deliver products with fewer issues in the long run. And so they kind of gave a list of different strategies to improve product design. So I thought it was very relevant for that question that I asked. The first one would be analyze product behavior early. The next one would be implement a get it right the first time strategy. Promote collaboration between analyst experts and designers. Now notice they say promote collaboration. They don't say give everyone a simulation tool. It says collaboration between experts within the company. And then also evaluate more design iterations in early design stages. So really it kind of looks forward and it says that simulation, we're looking to understand the physics of products early on in the design process. And there's a clear need to evaluate more designs and find design mistakes early. And all of this is aimed to reduce costs all around. So really, I think this particular survey was interesting because it brought back and made us think that we shouldn't assume that your company knows the value of simulation. So only 70% actually said that they should analyze product behavior early. And then even less said that they need to evaluate more designs. So don't assume that your company knows the value of simulation. And as CFD practitioners, it's really our responsibility to be advocates for the use and to be able to talk about why simulation is key to successful product development. And I really wanted to start with that before I jumped into things. So today's talk, I will go over some of the challenges that coupled solvers seek to overcome. I'll talk about the incompressible solver that ENGYS has developed. I'll talk a little bit about HELYX GUI and then leave you with a few take-home messages, all within 30 minutes. So it's a lot of content for that short period of time. The first one, challenges that coupled solvers seek to overcome. The first and foremost is budget. So limited time budget. A great example is built environment where there might be last minute changes or there might be frequent changes. And with that, you need to run simulations on many different wind directions. And we do this because it's ideal for greater insight about a particular design change. The next one would be cost limitations. The one that jumps out the most is for motorsport. F1 has regulations around how much total compute can be used by a team in between or during a different design phase. So there's really compute budgets that cannot be exceeded. Another challenge to overcome is complex physics. So multi-physics problems, for example, conjugate physics, multiple regions with heat and mass and momentum transfer and transport. actually gave a talk earlier this summer at the Open Foam Workshop on an extended multiphysics framework for modeling heterogeneous transport and reaction kinetics. You can find that video on our ENGYS CFD YouTube channel, and I think I've posted it on LinkedIn already. But you can find this video. So this physics is definitely something that coupled technology can solve. The next one is compressible flows. So aerospace industry is very concerned with the flow physics that result in very stiff numerical problems. For example, shocks. Here's an example of an Onera M6 wing that was solved with our coupled solver on a pointwise mesh. So we're talking about physics complexities and then time limitations. And coupled solvers can converge faster to enable more simulation in the same amount of time. Coupled solvers can converge faster to use less core hours. So if you're trying to reduce your compute budget on the cloud, and they tend to be more stable, and they're ideal for multiphysics and more stable for transonic and high Mach flows. So with that in mind, this is what I'm going to talk about today, each one of these different topics. So let me start with the incompressible solver. And before I jump into an actual case and show you a number, I think it's actually interesting to talk a little bit about the background of the coupled solver and what makes it different from a segregated approach. So here, if we start with the differential form of the steady state Navier-Stokes equation, here we've got continuity and we've got momentum. And right here, there's no source terms. We could have another source term for moving reference frame, or we could have porous media. And in the long run, we're going to linearize this nonlinear equation. So it's nonlinear in this term right here, but we linearize that to make a linear system of algebraic equations, which is about 3 slides ahead of you. We take the differential form, we turn it into an integral form. Here, I'm only showing the momentum equation. We're using closed surface integrals, so we turn a volume integral into a surface integral. And we're using these standard methods to discretize advection, gradient, Laplacian terms. Now, for the semi-discretized form of that equation, for a segregated solver, we treat some terms explicitly. So for example, the pressure gradient in our momentum equation, its contribution is treated explicitly and thrown into the right-hand side of the equation as a source term. We also have a separate pressure equation from Riccio interpolation, which we solve separately outside of this momentum equation. Each variable is solved separately, so ux, uy, uz, pressure. And this is really the standard pressure-based approach that most software use. Now, the semi-discretized form of a coupled approach looks very similar. However, now we have a pressure term and pressure contributions on the left side of this equation. And so we're trying to treat some of the source terms implicitly where possible. So the pressure equation isn't shown, but we do have some pressure equation, the pressure gradient contributions, treating that implicitly on the left-hand side. And we like this because this means that information between variables is more quickly communicated. So that means that in between iterations, that there's more information that's given back to the momentum equation to allow faster convergence. So what does this actually mean? If we look at the algebraic form, here we have the diagonal weighting coefficients, and we have the off-diagonal weighting coefficients of our variable x. And so we're solving an ax equals b system for each one of our ux, uy, uz component, and then also pressure. So we're solving 4 different algebraic systems, and it takes a lot of time. One of the main reasons we, I guess, like to do that is because in the past there were memory issues. It's tough to put all of this together on a computer, and so I think classically we treated them as separate problems, and it was easier to load it up onto and run it through a CPU efficiently. And we connect these 3 equations with pressure using Riccio interpolation. There's also an explicit pressure gradient. And again, nonlinearity still exists, but we've linearized the Navier-Stokes equation. All right. Now for the algebraic form of the coupled simulation, or the coupled approach. So back to the segregated, this is at each point in space, each cell center on the mesh. Now for the coupled approach, we have this 4x4 tensor at each location in the mesh. And at each location, we're solving a variable that has 4 different components. So ux, uy, uz, and pressure. And here we have the diagonal components, and then we have the off-diagonal components that we're solving. And then also on the right-hand side, we have the source term. So now we're solving one single ax equals b system. So it's a single equation system. The contributions of pressure right here with momentum and from momentum are integrated through a reach-out coupling inside of the equation itself. So the implicit pressure gradient is coupled directly inside of momentum. The nonlinearity still exists, but we have much tighter communication, much tighter coupling between these different equations. And so that's really the main reason why a coupled approach is different from a segregated approach, in that there's just tighter communication between these different variables in each point in space in the mesh. Okay, so what does that actually mean? How does that manifest itself in an actual result? Here we've got an open wheel demonstrator. This geometry was created by my colleague Thomas Schumacher, and it was for the Mantium challenge. Here we've got 2 different meshes. We've got a coarse mesh and a fine mesh. The coarse mesh is 22 million cells. The fine mesh is 88 million cells. We can see the difference between segregated and coupled solvers. We have an order of magnitude less coupled iterations required to converge in every case. So here we've got double precision on the coarse mesh. We've got double precision on the fine mesh, and we've got single precision on the fine mesh. We can also see that the total time between segregated and coupled is different, and the coupled converges faster in absolute time with any setup, any size of the mesh. And overall, the speed up ranges from around 3.9 up to about 4.6. In terms of differences between the actual results, we can see no difference between the two. So coupled and segregated give exactly the same answer, which is very nice. And it's something that we would expect. If we're looking at an integral value, so we're integrating over the surface of the vehicle and we're looking at total lift and total drag, we can see the red curve in both of these plots. This is the coupled, and then the dark blue would be the segregated. We can see that the coupled and segregated both converge to relatively the same value, and the coupled solver converges faster in both instances, or in both measurements. If you look at a turbo machinery case, so this geometry was provided by Grundfos. The mesh was generated with HELYX X mesh, so this is the native mesher inside of HELYX. The background mesh was 5 millimeters. Not terribly large of a mesh, so 1.2 million cells. And this was a pump with a sliding mesh. So here we've got a sliding mesh interface, which is this ring right here on the outside. So this part is rotating around, pumping water at around 2,900 RPM, K omega SST turbulence model at a particular flow rate. This was a transient simulation for a total time of around 0.6 seconds. This was run on ENGYS's cluster, which uses AMD EPYC chips. And here we're comparing the difference between an older version of the coupled solver and then the new version of HELYX Coupled that comes out in a matter of weeks. And so here we can see that in version 3.3, which is about to be released, there's a 42% less time required to get that same answer. So that's a pretty amazing result, because that means that we can pack more simulation in the same amount of time. Or we can use a larger mesh. So here we're looking at shaft power. Sorry, we were looking at efficiency here. Let's look at shaft power. We can see that the power actually converges very identically to a previous version of HELYX Coupled. We can see the head also converging to an identical value of a previous coupled solver. Let's look at another turbo machinery case. This is a centrifugal water pump. There's 6 blades. It's also 2,900 RPMs. And here we're looking at 5 different flow rates. This mesh was a little bit larger at around 10.6 million cells, and it used the new extruded algorithm that comes out in version 3.3. What's the extruded algorithm? Well, it's an algorithm that has been developed at ENGYS for layer addition, and it ensures 100% layer coverage on all components within the geometry. So it's ideal for things like turbo machinery. The CFD setup, it's a steady state problem with moving reference frame, also using a K omega SST model. And what we wanted to do was again compare a segregated solver to a previous version of coupled, and also the coupled solver in version 3.3. So here, if we look at head, coupling power, leakage, and efficiency, we can see that there's virtually no difference between the segregated and then the 2 version of the coupled solver. In most of these plots, there's a minor difference between a previous version of the coupled solver and the new coupled solver, but it's, for all intents and purposes, it's really identical between the 3 different comparisons. What's important is the speed between the 3. So here we've got this top red line, which is the segregated solver, the black line, which is the previous version of coupled, and then the blue line, which is the new version. So comparing the new coupled versus a segregated solver, we see around a 60% speed up between those 2 different approaches. We also see a 25% reduction in solution time versus the equivalent solver in 3.2. So this is 25% faster than the previous version. And then also we see a 30% reduction in memory footprint versus the equivalent coupled solver in 3.2. So we see, gains in speed that are also due to better memory management in this case. So what does that actually mean? If we put an actual dollar value to what we're looking at, and we look at maybe a 5 times speed up. So if you're running 32 simulations on 256 cores for 20 hours each, and we have a core hour cost of 0.2 euro or 0.23 US dollars, that would be around $37,000 in compute costs alone. And with the coupled solver, now those costs have dropped tremendously to around $7,500. So you've saved $30,000 in compute costs just from a 5 times speed up. Now, let's just say that you wanted to keep your budget of $37,000. Well, then you can run 5 times the amount of simulations. And so if we go back to my first slide, which I talked about, some of the best behaviors or some of the kind of tips that high performing companies gave, they said that running more simulations early on led to greater success of products that led to, lower costs. So here, we're actually lowering costs, or we're investing in our product by giving more simulation, more design time, trying to find more potential problems with that. But let's look at a 10 times speed up. Same thing. So we see a drastic reduction of costs, and I don't think a 10 times speed up is an outrageous thing to think about with a coupled solver. So here we can see more than a $32,000 savings, and then we can see 10 times as many simulations using a coupled approach for the same amount of core hours as we saw with our segregated approach. Now, remember also that open source solvers really enable running simultaneous jobs and running parallel jobs at no additional cost. So right there, we have a leg up on other commercial codes just for that fact alone. So there's a tremendous potential with coupled solvers to save time and save money. All right, great. So we hit on my first point of kind of the drivers for using coupled solvers. So let me talk a little bit about HELYX GUI. HELYX GUI is a tool that engineers are able to perform a CFD analysis from geometry import to surface manipulation, meshing setup, simulation setup, actually running the simulation, post-processing to create the results that you might generate for a report. The key strengths that HELYX offers is that it's a single cross-platform simulation environment. There's advanced meshing and physics, and the scale-up of core count can be done without a license, and the scale-out to unlimited simultaneous jobs also does not require a license. So this is a huge benefit for cost reduction within companies who need to run hundreds or thousands of simulations if you're doing a DOE to try to optimize a particular result. We have Python macros that are built into the GUI to allow for automation. We call it journaling, so you're able to actually record the journal. You record your steps in the GUI, and then you're able to automate the process based on some steps that you've already taken. To select what coupled solver and what coupled physics we need, it's very simple. Inside the setup tab, there's one tree entry for the actual solution state, and for a coupled state, you just select coupled, and you can select transient or steady, and then we select compressible or incompressible. So this is the incompressible state right here for the incompressible coupled solver. So some of the physical models and boundary conditions for each one of these. So for the incompressible coupled, there's access to the standard boundary conditions. And I mean standard things like total pressure inlet, fixed pressure outlet, volumetric flow rate coming in, mapped profiles coming in, or any other available boundary condition for an incompressible flow is available to the coupled solver. There's also moving reference frame. There's also generalized moving reference frame. So if you're not familiar with generalized moving reference frame, I actually did another webinar a few weeks ago on this when we applied a generalized moving reference frame to capture the physics of tire grooves much more effectively than just a rotating wall boundary condition. Also, there's porous media models, there's dynamic mesh motion, there's access to function objects to do things like in situ data processing, calculating Y+, calculating pressure coefficient, and then there's runtime post-processing, which is a really interesting feature that allows us to generate images that we can use for movies and things like that without actually writing out all of the data, so we can save a tremendous amount of disk space. So let me leave you with a few take-home messages. If I were to say a few things about the incompressible solver, I would first start by saying half of all F1 teams are using HELYX for meshing and coupled solvers. So this is because it's a huge reduction in computational cost per simulation. It enables more simulations for the same computational budget, and really it's ideal for turbo machinery, for built environment, for motorsport, for the automotive industry. It's a really game-changing tool for these different industries. With that, I'm finished, and I hope everyone enjoyed. What I'd like to say is that we are hosting a user group meeting in Detroit in September of 2021, and you can visit ugm.engys.com and reserve your spot. You can also visit there to see how the agenda updates. Thank you very much for joining me today.